This is section 7.1, area of a region between two curves. In this chapter, we're going to be talking about a variety of different applications of integration. And the first of those is the area of the region between two curves. I'm going to introduce a theme in this section that will be repeated for quite a while through this whole applications of integration chapter of how we build an integral for a given problem. So I'm going to remind you of how you found the area under a curve first and build up into the topic for today. So I assume in your Calculus 1 experience that you looked at functions that were non-negative. So something maybe like this, some function f of x, and you were asked to find the area under the curve from x equals a to x equals b. And when you first started this process, I'm assuming that you estimated that area using a simple figure, perhaps a rectangle. So I'm going to draw in a representative rectangle, and it's pretty big. Of course, we know that eventually we want there to be infinitely many of those that are really tiny, but I'm going to draw one that represents any of the rectangles anywhere I could draw, and it's pretty wide so that we can see it. And this one happens to be attached to the function on the left side of the rectangle. It could have been the right side instead. It doesn't really matter. As it turns out, it's no big deal. So there you have a second rectangle you could look at. But this representative rectangle is delta x wide. And we had a formula for finding the width of the rectangle. You find the width of the region, b minus a, and divide it by n, the number of rectangles. And that gives you the width of each rectangle. Then, to find the area under the curve, or at least an approximation of it, what you did was you found the area of your rectangle. In fact, if there were 4 or 6 or something, you probably drew those in at first and learned how to find the area of each of those, let's say 4 rectangles, and then add those up. That was kind of your first task. And what you needed to do at that point in time was figure out that the length of the rectangle is a particular output of the function. Remember how I said that the first rectangle I drew was attached to the curve at the left-hand side of it? And I'm assuming that this, let's just call this x sub I, where that left-hand position is, and f of x sub I is the height of that rectangle. And so the area of one, did I say triangle? I meant rectangle, sorry. The area of that one rectangle is length times width. Okay? And of course over here I would have attached to the right side, so my x sub I would have been on the right side for that one. But the idea is the same. Then you got an approximation of the area for the whole region. So this is the area of one rectangle. You found the area of the region, or an approximation of it. So I'm going to write approximately equal to here in just a second. Was approximated by adding up from I equals 1 from the first rectangle to the nth one, the generic f of x sub I, which means we're going to take each x, either left or right or midpoint or whatever was decided. We're going to find that x sub i's y value, that'll be the height of that particular rectangle, multiply it by delta x, and then add up all of the rectangles from the first one, I equals 1, to the nth one. So if it were 6, n would be 6. You'd have 6 products, length times width. which you would then sum, which is what the sigma denotes, is it's a summation of those things, and get an approximation of the area of that region. Then we talked about, well, what if we want the exact area? What could we do to improve our calculation? And what happened was, is if delta x made all of them exactly the same width, if we push the number of rectangles toward infinity, the error in our estimation decreased. And in fact, if we went all the way to infinitely many rectangles, we got exactly the area. And so what we did was, we did a limit of this Riemann sum. That's what this summation is called, where you have a product of things. Here, height of the rectangle times the width of the rectangle is what those represent. So, and we learned how to find this an even better way, because this limiting process of the sum, it could be denoted by a definite integral sign from a to b, x equals a to x equals b. F of x sub I became f of x in the integral, and delta x became dx in the integral. And that represented the exact area under the curve from x equals a to x equals b. Okay, so now that we've reviewed that, we know this is the beginning of the theme. What we do is we find some simple figure to estimate what we're trying to find, like the rectangle here. Then we come up with a formula for the area, if that's what we're trying to get, of that simple figure. Then we add up n of those to approximate what we're trying to find. And then we take a limit as n approaches infinity of that sum, and that gives us the exact area. Notice this is an equal sign, area equals here, not approximately equal to like I did above. And we represent the limit as n approaches infinity of a sigma notation. That gets absorbed all together into the integral sign from a to b, and then of course whatever you have behind that is what you're going to be integrating. In this case, f of x and then dx. All right. So let's now turn to what we're talking about today, and we will see this theme. We'll see this theme repeated many times, including today. But I'm going to start actually with a slightly different thing. These are supposed to be perfectly vertical and perfectly horizontal lines. Obviously, I am unskilled when it comes to drawing those things, so please pardon that inability to draw carefully. So let's say that I had a function, let's say f of x. Looks like this. And then I had another function, let's say it looks like this. And I want to find the area between those two things from x equals a to x equals b. So if I draw a line segment where x is a and a line segment where x is b, then I'm trying to find that area. Okay? That's my goal. So I'm going to use what we just talked about and see if we can understand how this works based on what we already know. Okay, so I could find the area under the f function from a to b, right? Let me extend these down so it goes all the way to the x-axis. I could find that, right? And that area would be the integral from a to b of f of x dx. Simple enough, using something we've already talked about. In fact, you talked about it in Calculus 1 pretty extensively, I would think. Then I could find the area under the g function from a to b, and that would be the integral from a to b of g of x dx. And what I want to find, of course, is the area that's between them. I'm going to label that with a red A, and that's going to be represented by the part of this that's shaded in red. So geometrically speaking, do you understand that the pink region and the green region sizes, the area under the F curve and the area under the G curve, if you knew those numbers, what would you do to the areas under the F, the pink area, and the area shaded in green to get the red answer? Well, hopefully you're thinking that you would subtract the large area that's in pink minus the green area, leaving the red. And that's exactly it. That's what we want to find out. So we have a property of integrals from Calculus 1 that I want to now employ. It's a reversal of a property that you know, but it works this way too. If you have integrals that have the same upper and lower bounds, so this is from a to b and from a to b, so they match, and the differentials dx and dx match, so that part has to be the same. Well, if you are adding or subtracting two integrals that have those conditions met, then you can combine them into a single integral from a to b and take that function from the first integral minus the function from the second integral dx. And that's the formula for the area between two curves, f and g, assuming, of course, that f of x is the larger of the two, or equal to. They could actually intersect. That wouldn't be a problem. On the interval from a to b. Okay. Another couple of assumptions that we're going to need to make sure that you remember from Calculus 1, and you may not have heard, this may not have been a great big deal at the time, because just like everything works, so why'd you have to worry about it? But in order for an integral to exist, let me go back up here to the one we already talked about. To be able to have a definite integral represent that area, f has to be non-negative, which I did say that, but what I also needed to say is that f must be continuous. On the interval from a to b. For this to work, that's a necessity. And when you don't have a continuous function, that's going to be and a and b have to be real numbers. They can't be infinity or negative infinity. And those are important conditions to be able to state that the definite integral exists as a value. So maybe that wasn't mentioned very strictly to you in your Calculus 1 experience, but it will become very important to us later in this course. So continuity of the function you're integrating is a super big deal. And we'll learn how to deal with that later when it's not continuous, or one of your bounds is infinity or negative infinity. Not trying to give away everything today, but that's one of the things we'll talk about a little bit later in the course. Okay, so I want to try to recreate that picture. I'm sure it won't be exactly the same. And it doesn't matter if they are, because the idea of what we're doing is actually what's important. So here's some function f, probably not the same as before. Pretend with me. And here's function g. And we're going from a to b. But instead of thinking of a subtraction of the areas of two regions to get the remaining region, so the total region minus the lower part gives you the part up there on top that was the part between the two functions. I want to go to the idea that we already talked about, and I want to make sure that this is very clearly understood what we're doing here. Instead of having the rectangle go all the way to the x-axis, what if I connected it to the functions? For the top of the rectangle, attach it to f, and the bottom of the rectangle, attach it to g at some x sub I place. Well, a really important concept that we're going to be using many times in this course is that anytime I ask you to measure the distance from the x-axis to a function or a curve or whatever it is, that is always a value of y. On the other hand, if I ask you to measure from the y-axis to a point on the curve, that's going to be a measure of x. Seems pretty simple, but it's critical that you understand that. So, coming back to this problem, the length of that rectangle is in question. I'm going to go ahead and say that for sure we would want to use delta x the same way we defined it above. So that's not an issue. My issue is, how do I find the length of that rectangle? Well, if we measured from the top of that rectangle, which is where it touches the f curve, down to the x-axis, of course that's a y value. Now we're going to have two y values here, so we've got to be careful that we call it the right one. And if you had a calculator, you might call it y sub 1, because that's the notation you see in your calculator. But that one happens to have a name, so we're going to use f of x sub I. Okay, f of x sub I. So we're at the ith rectangle. That's the x coordinate that's producing the values of y on those two curves. And so the distance at x sub I from there at the x-axis up to function f is f of x sub I. By the same reasoning, the distance from that point where the rectangle touches the g curve to the x-axis is a value of y. And I very well might call that y2 if I had a calculator, but because these functions are named, we'll say that that is g of x sub I. And to find the distance from the point on the curve g to the point on the curve of f, what we'd want to do is, well, and I'm going to say this because you may have already figured it out, and that's great if you did. But sometimes if I can't figure out something, I'm going to make up numbers, even if they don't make total sense to someone walking by just looking at this and might go, what are you talking about? Anyway, I'm going to pretend, for example, that this y value on f is, say, 10, an easy number to deal with. And that the number on g is smaller, so let me just say it's maybe 7. How far is it from 7 to 10? Well, it's 10 minus 7, right? 10 minus 7 would be the distance, so it would be 3 long, right? Well, let's use that idea. Instead of 10, it's f of x sub I, okay? So this is the f of x sub I number. And instead of 7, we have g of x sub I. So g of x sub I is like the 7. So to get that distance, we're going to subtract our f of x sub I. I can find a place to write this. I've crowded up the picture so much, it's terrible to see. So this distance is going to be f of x sub I, our example was like that's 10, minus g of x sub I, and our example of that was like, what if it's 7, to get that distance. And so the length of the rectangle is f of x sub I minus g of x sub I. That's the length, times the width, delta x, produces the area of each rectangle that would span the distance from G to F. Then we'd want to add up all of the rectangles from the first one through the nth one to get an approximation of that area. Now, to get the exact area, we would want to take the limit as n approaches infinity of that Riemann sum. Always like that guy's name, Georg Friedrich Bernhard Riemann. It's just so cool to say, Riemann. Anyway, now back to Texan, Riemann instead of Riemann. We would take the limit of this sum of the area of our representative rectangle, adding up from the first to the nth one, and that limit as n approaches infinity can be replaced by the definite integral from x equals a to x equals b, and this time our function is f of x minus g of x, and delta x becomes dx. And you'll notice, if you look up above, that's exactly the same formula we got by the subtraction of the areas using something we already knew in geometry. Now, this second approach is the one that we're going to see repeated over and over again for all kinds of applications. Again, I found a rectangle that went between the two functions, found a formula for the area of that rectangle, added up many rectangles from the first to the nth one to approximate the area, and then did a limit as n approaches infinity of that Riemann sum, and arrived at a definite integral to express that, in this case, area. I keep saying in this case area because it's not always area that we're finding. In this section it is, but in later sections it's not. I'm trying to apply a theme to this so that you get that. Okay, so that takes us to area of a region between two curves. It's a box there that says, you know, what that is, and it defines everything very well. I tried to say everything, but hopefully I got everything. If f and g are continuous, I did say that, on the interval from a to b, and g of x is less than or equal to f of x, that's to establish which one's the top one and which one's the bottom one, if you will. For all x values in the interval from a to b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is that definite integral that we established. And so that is our area formula for the area between two curves, right there. That's it. So that's something you would want to commit to memory. That's an important result of the work that we've done. All right. Now, what's interesting is that if I looked at that region that I drew there, and if I shifted the whole thing down 400 units, I'm exaggerating, of course, if I moved that way down and everything was below the x-axis, do you realize that the size of that region between them would not change? And so if we moved it way down, and let's just say that those numbers became -3, I'm not going to go down as far as I said, for the top one, oops, I should probably color code that. So the top one would be, let's say, -3, that's an f value. And the lower one was like -12. And of course that's a g value. Would, since f is the higher one, the one with bigger, larger y values than the y values of g, -3 is larger than -12. Could I get the distance from -12 to -3 by subtraction like we did before? What would f minus g equal? Well, that would be -3 minus -12. And of course, subtraction of a negative makes that addition. So -3 plus 12 is 9. Yes, that finds the distance between them. And that distance is 9. And so this formula does not have to have functions f and g that are non-negative. The area between two curves, whether it's positive or negative, below or above the x-axis, this formula works for all of them, even if one's positive and one's negative. So there's some pictures in figure 7.4. I hope I copied that for you in your notes. That shows that same region with the, moving it down so that g, for the most part, is below the x-axis and f is above. The distance between those wouldn't change, and so the area between them would not change. And even if both f and g were below the x-axis, as I was trying to represent with my -3 and -12, the area itself would not change. So one of the things that we're going to encounter, and I kind of gave this away a bit earlier, I don't know if you heard what I was saying, but a lot of times we're going from y value to y value. And that means that our representative rectangle is going to be vertical, okay? And that means that its width is delta x, and the length of it is going to involve y things. Like in above, it would have been f of x minus g of x. I'll just write that down as an example. That fits with what we were just talking about. However, there are times when it's better and easier to use a horizontal rectangle whose width is delta y. And this is going to be x stuff. I'll just say x of y. It'll be x, well, I don't know if you know that notation, so let me back up. Let's just say that this is, let me back up even further. It will be x stuff, where x might be defined as f of y, and that's x sub 1, and x sub 2 might be defined as g of y. And so this expression might be something like f of y minus g of y. That's an x thing minus an x thing. Just like this over here to the left was a y thing, f of x minus g of x, a y thing. So let me kind of write that a little bit more completely so that you understand what I'm talking about. It is the difference of two y's, but we're calling them by different names so we know which y we're talking about. That's why we use the names f and g. Okay, so that's going to happen sometimes, and you need to realize that that's possible and sometimes desirable to work with it that way. So just wanted to give you a heads up that that's going to happen at times. All right, so let me see, what do I want to talk about next? Yeah, okay, well, that's right. Well, and let me just say that this integral would be maybe, in fact, I'll write a version of the above integral if you had things as defined as x equals a function of y. That integral would be from c to d. Okay, so whenever we're measuring from x equals something to x equals something else, like from x equals a to x equals b, we use the letters a and b generically. If we had, for example, something that looked like this, let's say that this is f of y, and something else, maybe this is g of y, then the distance between those would be, for a representative rectangle, draw that in a different color, for a representative rectangle that would be delta y in width, the length of that would be f of y minus g of y. And we would be told to find the area between y equals c, from y equals c, so there, to y equals d, so there. And so we're finding the area of this region here. And that's our representative rectangle. That's delta y in width. And so the formula, back to what we were talking about, the formula for that would be the integral from c to d, from y equals c to y equals d, of f of y minus g of y. And delta y will become dy, the differential dy. And that's the same formula, but with rectangles perpendicular to the ones that we normally think of using. I hope you did some integration with respect to y in Calculus 1, because it's really important, because sometimes you just can't do it in terms of x for whatever reason. And so I hope that this is not a strange thing to you, that you've seen this before. If not, hopefully it's not that hard to understand. All right, so let's do an example. We're going to find the area of the region bounded by the graphs of y equals x squared plus 2 the line y equals opposite of x, the vertical line x equals 0, and the vertical line x equals 1. My suggestion to you is, as much as you can, draw pictures. Now, if the functions are as easy as this, you should probably assume that this would not be one where you'd need a calculator, and probably I would not allow you to use a calculator for some questions on the test. So this is a good example of that. Pretend like you can't use your calculator, put it down, set it aside. We can do this. All right, so you should know, of course, what those two curves look like and how to draw them fairly accurately. Okay, so x squared, y equals x squared is a parabola. The plus 2 moves it up 2 units. So the vertex will move from 0, 0 up to 0, 2. The point at 1, 1 will move up to 1, 3. Negative 1, 1 will move up to negative 1, 3, etc. And for our purposes, that's probably enough clarity for where the curve is. We know what it's supposed to look like. So I'm going to allow a non-perfect graph to be represented here. That's perfectly fine. I didn't mean to leave gaps there, but you can still see those points, so I guess it wasn't too bad to leave those gaps. It is a continuous curve. So I just wanted you to be able to see those points. Let me fill that in, sort of. Okay, so that it looks like I am graphing a continuous curve. That's a little bit better. Okay, that's the graph of y equals x squared plus 2. Y equals the opposite of x, has a y-intercept of 0 and a slope of negative 1, so go down 1, right 1, or up 1, left 1, and draw that line. Wish I had a straight edge, that would look a whole lot better. Oh well, good enough, I suppose. And the vertical lines, x equals 0. Well, wait, I gotta change my color, hold on. You can't see that. X equals 0, which is the y-axis, and x equals 1, which is the vertical line right there. Well, wow, that does not look straight. Okay, at any rate, this is the area of the region we're trying to find. Okay, so if we draw a representative rectangle, and I'm going to take back that shading because it's going to get in the way of my drawing a good picture. You won't be able to see much, so just pretend like that shading's there, but I don't want to look at it. Draw a representative rectangle from one curve to the other, anywhere. And it can attach on the left side, right side, anywhere. Just so you know that it does attach to the curve at a particular point. The width of this one is delta x. And this is the area between two curves. So we should be able to use what we just learned. Let me say that not mathematical language, but day-to-day language, this is pretty good. Let me go back up here for a second. This formula of f of x minus g of x, when I'm doing that, I'm actually thinking top function minus bottom function. Not mathematical, but certainly makes the point as to which one is which. And in the delta y example, that one will be thought of as right, the rightmost one, minus left. And that'll help you make sure that you subtract in the right order. Okay, so looking at our picture, and this is one reason why you want the picture, is to make sure you determine which one is the upper function, which one's the lower function. Knowing what we know, this area is, according to the formula up above, not the one with c and d, but the one with a and b, is the integral from lower bound 0 to upper bound 1 of the top function, which is x squared plus 2, minus the bottom function, which is the opposite of x. And I know that'll turn into addition in a second, but the formula is top function minus bottom function. So I always want to start that way, dx. So simplifying, and some people can't stand that I write these out of order, but I'm going to do it anyway. A lot of you want me to write plus x between the x squared and the 2 because you just can't stand them in non-descending order. And I kind of blame your Algebra 1 teachers for that because they made you always rewrite them that way. And it is a good way to write them, like if you're going to factor. You've learned how to factor things in descending order, and it's easier to deal with. So I get it, but I'm just not going to do that. Now, to evaluate this integral, and remember we're not using our calculators, to evaluate this integral, we're going to use the fundamental theorem of calculus, which states that if we have a definite integral to evaluate, we're going to find the antiderivative function for our function. And the normal way to write the antiderivative of function f, which is a lowercase letter, is to write capital F of x for its antiderivative, and then evaluate that antiderivative function from a to b. Then that means that you substitute b in first, then subtract the substitution of a into your antiderivative function. That's the fundamental theorem of calculus. And that's something that you need to know and be able to use. Of course, you've done it a lot, but I just wanted to reiterate some things that you learned in Calculus 1. So the next step would be to find the antiderivative. So we increase the power of x by 1 and divide by the new power. I'm hoping this is not a surprise to you. The antiderivative of the constant 2 is 2 times x, or the constant times x, plus increase the power by 1 to x squared and divide by 2, the new power, so that's 1/2 x squared. Part of the reason I'm doing this is to review Calculus 1 and antiderivatives. You're supposed to have mastered them in Calculus 1 and have them all at your beck and call. So at any moment, if I said, what's the derivative of cosine of x, you'll remember what it is as needed. But anyway, so you'll see me doing some Calculus 1 level stuff because I will expect you to be able to do it. So I want to see that antiderivative. I want to see that 1/3 x cubed plus 2x plus 1/2 x squared, because that's telling me that you know you're doing the fundamental theorem of calculus. Then I want to see the substitution of the upper bound in to that antiderivative function. So in other words, I really don't want you to simplify yet. I want to see the substitution minus the substitution of the lower bound. We're going to start with the 0 calculation because that's the easier one. Then I'm going to give you an admonition because people make this mistake a lot, so let me just say this early on. If I cubed 0 and multiplied that by 1/3, and 2 times 0 is 0, I mean, we're getting 0 plus 0 plus 0, right? And the final answer is that that last part is just minus 0. So it doesn't have an effect. And so you may get complacent and think, well, whenever I'm substituting in 0, I'm always going to get 0, so why bother? Well, I beg to differ. What if it's cosine of 0? Is that 0? Nope, that's 1. What if it's e to the 0? Is that 0? Nope, that's 1. So don't become complacent and think substitution of 0 just automatically gives you 0. That would lead you to a lot of error. And I really don't need to see your arithmetic. I was showing the minus 0 to make that point about substitution of 0 doesn't always make it minus 0 at the end. So I don't really need to see this line I'm writing right here. I'm not really that worried about it. So this ends up being 17/16 minus 0, which is 17/16. Oh, I'm sorry, 6th. What did I say 16th for? Or why did I write it? 17/6. Pardon me. Okay, and that line I just wrote, the 17/6 minus 0, I don't need to see that line. I really don't care about that. I really don't need to see arithmetic. If you want to write it down, just for your own peace of mind, if you don't have a calculator and you just want to make sure that you're doing it correctly, by all means, write all the stuff you need, but I won't be grading that line. I'll be grading, did they write the antiderivative, right? So, did you write the antiderivative? Check. Did they employ the correct use of the fundamental theorem of calculus by substituting in the upper bound minus the lower bound? And then I'm going to check your answer. Oh, and the other thing I'm going to check is, of course, your setup, that you set it up correctly. You have a correct integral that will find what it is we're trying to find. So those are the gradable items. In fact, that second line where I changed minus negative x into x, I don't really have to see that. I mean, probably I would even write that if I were you, but I'm looking for a definite integral that does what I ask you to do. Then I'm looking for the antiderivative. Then I'm looking for a substitution of the upper bound minus substitution of the lower bound, and then an answer. Those are the things I really find important. Those are the calculus pieces of this, including the answer. I think the answer point, even though it's just arithmetic, is important because, you know, if you're trying to measure something and you tell someone the wrong size and they buy paint for, you know, this number you gave them and it's not like half as much as you really needed, well, the answer does matter. So I don't want to neglect that. The answer, of course, is an important part of this whole process. All right, so another thing that happens, notice that these two graphs up here, y equals x squared plus 2 and y equals opposite of x, didn't intersect each other anywhere. And sometimes the more common problem is when you have intersecting graphs. So that'll be the next thing that we conquer. So let's look at two graphs that intersect. Let's do, how about f of x equals 2 minus x squared again, a graph I think you should be able to do without a calculator, and g of x equals x. I want the area between those two. Notice I didn't mention x equals a and x equals a to x equals b. I'm not mentioning that. I just want the area between them. And when you graph it, that will make more sense. So the area between those. Let me see. Get my axes all set up here. All right, I think that's good enough. All right, so let's graph 2 minus x squared. That's a parabola that has been reflected over the x-axis because of the subtraction there. The negative 1 times x squared reflects it, and then it's been shifted up 2. So that puts the vertex here, and a couple of our points there and there, and that is enough to get the idea of what the parabola looks like. These graphs, by the way, are not intended to be perfect renditions, and I'm not going to grade your graphs here unless we have a unit on graphing something. This is just a thinking piece, something you're going to be thinking about and using. Okay, then y equals x is going to be this line, intercept 0, slope 1, and I want the area of the region between them. I'm going to shade it, and then I'll erase the shading like I did before. There's a real advantage over chalkboard or whiteboard. I can erase stuff easily. So that's the area we're trying to find. So saying the area between them is sufficient. That's the only time that there's area between them, is from one point to the other. Well, all of a sudden, that means that the points of intersection have become important. I'm going to need to know the coordinate of this point of intersection and this point of intersection. Now, because we just graphed those and I had some very specific points that I plotted, I'm pretty darn sure that this one is at 1, 1. And I could guess that that's at negative 2 something, probably negative 2, negative 2. That's why, but I don't know that for sure until I do a little bit of investigation. So even if you don't know by having graphed the actual points that you cross through both graphs at that point, like 1, 1, what we would do to find the points of intersection in a general way is that we would set the y values equal to each other. That's when they intersect, is when their y's are the same number. By substitution, that's 2 minus x squared equals x. Now, to find a solution to this polynomial equation, you're going to want to get this polynomial equation equal to 0. So I'm going to add x squared to both sides, and I'm going to subtract 2. Notice that I did write it in descending order this time, and that was on purpose because I'm about to factor. So I hope that when I have a polynomial equal to 0 that I do know how to factor it, because that makes the solution process way easier. I'm thinking of factors of negative 2 that had to be positive 1. Of course, that's positive 2 and negative 1 that do that. And so if that product is 0, we know that one of those factors at least is 0. So if the first factor is 0, x plus 2 equals 0, that means that x is negative 2. And if x minus 1 is equal to 0, we know that that means x is positive 1, which of course confirms the 1, 1 point that I found earlier is actually accurate. So this is actually at negative 2, and the y value is negative 2, which actually doesn't matter to me that much because it's the x that I'm concerned with. So what is the answer? Well, since we're finding the area between two things, the only new thing was having to find the points at which they intersect. We're going to go from x equals negative 2, the leftmost point of intersection, to x equals 1, the rightmost point of intersection, and then do, again, top minus bottom. So it's really important, and I probably should have labeled these better. The green one was G, and the pink one was F. And if I don't do that, please notice that I'll probably have to go back and do that so I know which is which. Anyway, so the integral will be of the top function, the f function, 2 minus x squared, minus the bottom function, which is x, it's the green one, g, dx, and then do the integration. Now, a lot of times if I just in a problem that's sort of like this, from now on, for this problem to continue it is a lot like the first one we did. It's quadratic, its antiderivative will be a cubic function, and we'll do substitution of top minus bottom. And so a lot of times what I'm going to do in notes is say, well, here's the answer, and for practice you should stop the video and go and double check that that's the answer you get. So I'm not necessarily going to go through every step, especially if it's a repetition of a concept I just covered. I mean, almost verbatim, it's almost the same function. I know it's not, but it's close. So go ahead and do this, come back and see if that's the answer you got. Okay. Example 3. Set up an integral expression. That's actually kind of important because sometimes, like the very first problem we did, where I forced you to write a good integral, show me the antiderivative, show me the substitution of upper bound minus lower bound, and then the answer. Sometimes I'm not going to be testing you necessarily on your Calculus 1 prowess, but on what you've learned recently. So if I say set up an integral expression, or set up an integral, that's all I want you to do. Okay? Don't find the antiderivative. Don't do the substitution. Don't find the final answer, unless I ask you to. So when you see that, I'm just going to be grading your integral and see if your integral is okay. Then, if I follow that up with then approximate, using your calculator, well, then you're going to type that integral into your calculator and evaluate it. And I'll go through how you do that in just a minute. So I'm having you skip in this problem. You're going to go straight from the integral expression to the answer. You're not going to show me an antiderivative, nor will you show me the substitution of upper bound minus substitution of lower bound. So I'm intentionally skipping some Calculus 1 that I could be asking you to do. All right, anyway, x is equal to y plus sine of y. You all know how to graph that, right? No, you don't. Don't lie to me. You don't know that, I'm sure. We'll see. Maybe you do. And x equals 2 minus y squared. That one you probably should be able to graph without a lot of muss and fuss and bother. So, speaking of calculators, I told you we're going to be using a calculator, so you may use one for this. But have you graphed a whole lot of things that were x equals a function of y? Probably haven't done that much, have you? Well, let me teach you how to do that because it's kind of cool and uses something you learned in pre-calculus quite nicely. So this is a nice little side trip into pre-calculus stuff, but you'll enjoy it, I'm sure. Do you remember parametric equations? Parametric equations are what you use if you want to introduce a third variable called the parameter to express x in terms of that parameter and y separately in terms of that parameter. And we're going to use the easiest version of that, which is if the parameter is t, which is pretty typical. If I let x be t plus sine of t and define y to be t, obviously by substitution, if y and t are the same, if you substitute it into your x equation with what t is equal to, you get our equation. And so these parametric equations will graph that relation. And I call it a relation because it's not a function. It doesn't pass the vertical line test, as you'll see in a minute. So if you go to your calculator, go to Mode, go to the Mode, which is right next to your second button, and go down and change it to parametric, which on my calculator is abbreviated PAR. Yours might have a longer word there, but it's parametric mode. And then when you hit y equals, you'll get x equals something in terms of t and y sub 1 in terms of t is equal to something. And that's where you'll type for x, t plus sine of t. Please make sure you're in radian mode. In calculus, we're never in degree mode, so might as well get used to that. And for y sub 1 of t, write just t. And t, by the way, is going to be what you get if you hit the xt theta n button. In whatever mode you're in, it'll give you that independent variable automatically. And while you're at it, we can graph the other one parametrically as well, although I think you should be able to do this one without a calculator. In fact, I'm going to do this one in a second without a calculator. So call this x equals 2 minus t squared and y equals t. So that would be your number 2 parametric equation. And then if you hit window, you'll notice that you're in control of what t values you're going to use, t min and t max. Basically, you want to use all real numbers whenever you can. Of course, you can't go from negative infinity to positive infinity because you can't type that in your calculator and it'll be a big waste of time. So what I'm going to ask that you do is, let's assume that t min, let that be negative 10. It may not graph everything that you want to see, but it's usually a pretty good estimate. And t max, let's just make that 10. And make your t step 0.1. That means that you're going to start at negative 10, calculate x and y, and plot that point. Then you're going to move 0.1 to the right to negative 9.9, substitute that in and find for t, and find your x and y, plot that point. And so it's going to step by 0.1s. And you're going to do negative 10, negative 9.9, negative 9.8, and calculate all those values and it'll plot all those. Then your x min, x max, and all that stuff, that's the normal physical window that you'll see. So for that, I'm going to suggest that you hit zoom 4, which is my favorite window, and see if you can see the graph. And if not, you can always go back to the window and change the physical window by changing x min and or x max, y min and or y max. And if you see like part of a curve, just for a minute, go back to window and change it to be from 0 to 10 instead and see what happens. I'm doing this too, so that's why the great big pregnant pause is happening, because I'm typing just like you are. And well, for one thing, I don't see enough of that to really make me feel like I know what it's supposed to be. So for one thing, I'm going to change the physical window, maybe go from like negative 10 to 10 for the x's, and for the y's, maybe go from negative 6 to 6. Just making up stuff. And hit graph and see what you see. Okay, I see a little bit more of the curve. Now, that's not the entire curve because we started with t equals 0. Go back and make t min negative 10 again and hit graph, and you'll see. And it apparently goes from one edge of the screen to the other. So that's basically, as far as you're concerned, negative infinity to positive infinity, just using t min equals negative 10 to t max equals 10. And those can be altered. Whatever you need to do, just do that. So that graph on the calculator looks sort of like this. See if I can mimic what I see. Well, it's not perfect. I can already tell it's not great, but that's okay. We'll get enough of it, close enough. Okay, so I'm going to call this x1 because they didn't give me a name of a function. I'm going to call this the x1 graph. Then the other one, which is one I think you ought to be able to graph without using technology. So I'm just going to review that really fast. So I'm going to need to put a scale on here, which may mess up my other graph because it may not have been done on the same scale. But the ideas are good. Okay, so x equals 2 minus y squared. That's a parabola that y squared opens to the right. When you multiply it by -1, it reflects it over the y-axis and opens to the left. And then the 2 shifts it 2 to the right. So it's going to be here, and then there's going to be a point here and a point here. And the parabola is going to do something like this. Again, probably not perfectly drawn. And so if you do this on your calculator, you'll have a better version of this than this one. I promise you, this is not a great picture. But anyway, I'm going to call this x sub 2 so I can remember which one's which. Okay, so unfortunately I have a very small picture, and so I would suggest that once you get your calculator all set up and you're happy with what you're seeing, this is the part of it that I'm interested in. Is this part of x sub 1, and I'm drawing it bigger, by the way, like I'm zooming in on this. And again, this doesn't have to be a perfect graph. It looks something like that for x sub 1. Now, for this one, I'm sorry, that's x sub 2, my bad. Wrote and said 1, it's x sub 2. For this one, there are a couple of clues, because x is given as a function of y, like x is y plus sine of y. That's a really big clue that we should be using a delta y rectangle. So here's a representative rectangle that goes from one to the other, and it's delta y. And the integral, therefore, will be, for the area between them, the definite integral from, oops, I don't know where those two intersect. And so I need to find that. So to find that, I'm going to set x sub 1 equal to x sub 2, which is where they will intersect. Their x's will be the same. So by substitution, that's y plus sine of y equals 2 minus y squared. Well, unfortunately for us, that is not something that you know how to solve algebraically. A mixture of a polynomial and a trigonometric function is typically not something that you would be able to solve using your normal algebra techniques. And so, good thing we have our calculators, because this one is one that we would solve with a calculator. And this is how I would do that. I would add y squared to both sides, and I would subtract 2 from both sides to get that expression equal to 0. And it's really important that you get it equal to 0 for the calculator version of solving this. Now, unfortunately, the parametric mode, you can't find where they intersect. So go back and change your mode back to function mode from parametric, and go to y equals. And although those are y's in that equation, we're going to type x's because our calculator only lets us use in function mode x as the independent variable. Of course, it's just a dummy variable, so what would it matter? So in y1, I'm typing x squared plus y, or I'm sorry, plus x is what I'm typing, plus sine of x, close parenthesis, minus 2. And whatever that graph looks like, let's say it looks like, in fact, I just graphed it, so I'm sort of cheating. This is what it actually looks like. Let's say it looks sort of like this. Well, when that graph is equal to 0 means the y value on that graph, because remember, we graphed this as y equals a function of x, right? It was x that we were using in the calculator. So it's interpreting whatever x is on the calculator is our y answer. Well, that's equal to 0 at the x-axis. The y value of that's equal to 0 at the x-axis. So we're looking for these two x-intercepts. And those will be our points where these two graphs meet up here. This one and that one. Okay? So to do this on your calculator, right now look and see where you think they are. I'm looking at the leftmost one, and to me it looks like it's between -3 and 2. I'm sorry, -3 and -2 is what I meant to say. So, follow along, type this. You should have your graph in function mode, y equals x squared plus x plus sine of y sine of x close parentheses minus 2 in your calculator and graphed it. Now hit second, calculate, and see the second option is 0. The x-intercept, another name for that, is called a zero of a function. It's another name for the x-intercept, is the zero of a function. So we're going to use that command. So pick number 2, and it's going to say left bound question mark. Well, what they're asking us for is between what two numbers is our x-intercept that we're looking for. So we said it's between -3, which is to the left of it. So for left bound, type -3, hit enter. Then it's going to say right bound equals, and type something to the right of it, like -2. That's why I had you figure that out beforehand. Hit enter, and it's going to ask you for a guess. It doesn't matter what number you guess. I actually just hit enter using the last thing I typed, -2, as my guess. I just hit enter, and it says that x is -2.242 about. So, coming back up to here, I just found that one of my answers, which is really y, right? We called it x in the calculator, but it's a y value we just found, is -2.242. And when you're rounding in class, I'd like for you to use 3 numbers after the decimal point, like I just did. But you want to keep the entirety of that number. So I would store this in my calculator. So to do that, hit second, quit. Then type x and hit enter, and you'll see that number with even more decimal places than you could see in the graphing screen. Then hit the store button. That's STO with an arrow. It's right above the on button. Hit the store button and type alpha, which is the green button, and then math, which is A. And that'll store it into A. So I'm going to make a note to myself that I stored this one in A. That means I have all of the accuracy that my calculator can get instead of only 3 decimal places of accuracy. Okay, now we're going to repeat that process to find the other one, and we're going to store it in B. So, hit graph again. This other one appears to be between 0 and 1, but if you're not sure and you want to just be safe and say it's between 0 and 2, I'll go with that. Actually, 1 would work, but let's just say you decided you'd be safer to go with 2. So, hit second, trace, which is the calculate menu, choose 0, number 2. The left bound, we decided on 0 is to the left of it. Right bound, we're going to type 2. And guess, I'm just going to hit enter. And it's going to give me a value of 0.752, rounded to 3 decimal places. Okay. Now, to store that into memory, we're going to hit second mode, which is the quit button. Type X and hit store, then green button alpha, then apps button, which will put it into B, hit enter, and that stores that number into the memory location called B. All right. So, a lot of graphing calculator stuff you may have never done before, which is good that you're getting this exposure to it. You needed to see it at some point in your life. Okay, so our integral will be from -2.242 is the lower bound. If you've declared down below that you're calling that A, you can write the number -2.242, or if you want to and you want to say A to B instead, I'm okay with that because you've defined A and B down below, which means, by the way, that I don't want A to be necessarily what I call the area, because I might be using A for a different purpose. So to be a little bit more accurate, I'm going to use a longer description than a single letter. I'm going to say area equals, just to be on the safe side, so nobody thinks I'm mixing up what A's value is. All right, so We're in this case, since it's a delta y problem, that's going to be right minus left. So which one's on the right? It's the pink one, which is x sub 2. So that's 2 minus y squared. Let me move that up a bit so I can make sure. Yeah, that's what it says. 2 minus y squared. That's the rightmost one. Minus the left one, which is x sub 1. And that was y plus sine of y. I hope you notice the use of parentheses to protect these expressions that are themselves two terms or more. You need parentheses to protect, especially behind the subtraction, times dy. Okay, that is an integral expression. You do not have to distribute the negative. If it were possible to do so, you do not have to collect like terms. You don't have to do any of that stuff. You just have to set it up. So that's what I'm looking for the first part of this problem, is that integral. And the a and b that you have there have been defined somewhere in your work, like I did down here. Okay? Oh, by the way, if you're having to solve for the point or points of intersection, I'm going to want to see that you've equated the two expressions with each other, and then I want to see the answers. I don't necessarily need to see the work on how you got those. If you used algebra, if you used a calculator, I really don't care. I just want equation that if you solve it correctly, you'll get the values negative 2.242 and 0.752. Okay. So then the directions say approximate the area using a graphing calculator. All right, to do that, I'm going to teach you a couple of things that you may have never seen before, so hold on tight. So here's something you may have seen before, you might not have. If I ask you to calculate the derivative of x squared and then evaluate that when x is 7, that's one way to write it. Another way you may have seen it written is if y is, no, sorry, I'm going to change my mind. If f of x is x squared, what is f prime of 7? Those two things mean the same. Those are exactly identical. One is using an evaluation. This vertical bar means to evaluate the expression in front of it using the value to the right of it. That's pretty commonly used in more advanced math. You've probably seen the one I wrote below with function notation. There's nothing wrong with either one, but one of them matches what you'll see in the calculator. That's why I said all that. So from the home screen, hit math, then go down, way down in the math submenu of math, until you find Nderiv. That's an expression that means the numerical derivative of something. So what it's doing is it's doing an approximation technique. And it's not necessarily perfectly the answer, although if it's supposed to be 5 and it calculated 4.99999999999999992, it's going to round it to 5 in this screen. So it'll look like it's exact. But nevertheless, hit that button. It's option 8, by the way, which you might want to memorize that because you may use it multiple times. And notice that it came up with this notation. So the first box below the D, and it's D box, type X. Then it's going to leap into the function, so type x squared. And then use your right arrow key to move into the box where it says x equals and type 7. Now before you hit enter, what is the derivative of x squared? 2x. And if you put 7 in for x, 2 times 7 should be 14. Hit enter. Voila, it's 14. Okay? Now, some of you, when you hit that key, math 8, you didn't see that. You saw a command nderiv left parenthesis. Well, I'm sorry. You don't have the newest operating system on your calculator, and you might not see what we saw, some of us saw. So what you'll have to do instead is type, after this, type first the function, then a comma. The comma is right above the 7. It's a button of its own, right above the 7 button. Then x, because that's like the dx, that was the first thing we typed, comma, then 7. So it's the function, the variable of that function, and the number you're substituting into that derivative. That's how you would access that. Okay. Now, there's also, if you go back to that math and then go down to where you see numerical derivative, go just a little bit further, and you should see F in INT, math 9, another one that you probably will want to memorize. Math, then hit 9, and it gets you this. Well, if you type the 9 or hit enter when you're hovering on the 9, you will see a definite integral symbol, just like what we see in math, unless you have the old operating system, and you won't see that. So for those of you who have the new operating system, you see a regular interval. So the lower bound is A. Luckily, we stored that. So in the first box, the lower bound box, hit alpha A, then hit right arrow to toggle to the upper bound. The upper bound is B, so type alpha apps, which is your B, then right arrow over into there. Then we need to type this function up here that we have. So if you want to simplify a little bit right now, that's okay. I'm going to distribute that negative. So I'm going to type 2, I didn't write the left parenthesis, minus x squared, because in the calculator your variable is going to be called x. So just get used to that. Minus x, and then distributing the negative, minus sine of x, right parenthesis. And I've finished the function, so hit right arrow key, and it's D box, hit X, and hit enter. And that's going to give you the numerical value of that definite integral as accurately as your calculator can do it. So you should have gotten 5.673. Remember, we're rounding to 3 decimal places. And of course, since the directions asked for that answer, that's something I'm going to look for. Okay, now some of you who unfortunately don't have that new operating system, what are you going to type? So let me go back down here and tell you what that is. So you're going to type the antiderivative. I'm going to pretend like it's x squared because that's really easy to type. Pretend like we're doing x squared, but that's the function you're integrating, comma, x, that's your differential variable dx, comma, your lower bound, which you type in your alpha a, or a number. If it were like from 2 to 7, you just type 2, comma, your upper bound, which we stored in as b. Of course, x squared won't work, so please be aware of that. So you don't want to type x squared, really. If you're trying to find the 5.673, you don't want to type that. You want to type what I said before. So I'll just say what that is. 2 minus x squared minus y minus sine of y. Oh, dang it. I started saying y because I was looking at something above. Remember, in your calculator, the independent variable is going to be x. So minus x minus sine of x is what will go there. Okay, so math 9, if you have the old operating system, first thing you type is the function you're integrating, comma, x, comma, lower bound, comma, upper bound. I really hope you have the new operating system because it looks mathy. It looks correct, mathematically speaking. It looks like a definite integral. And this notation right up here that I introduced, maybe you never saw that before, maybe you did. That's actually a common notation for evaluating a derivative of a function. So, and that's basically what that looked like, was that kind of look to it. All right, so hopefully you followed all of that. And if you have any questions, that's what class time is going to be used for, is to go over anything in here that you weren't sure of or didn't understand or want me to go into deeper, or some algebra I skipped that you want to see. Anything like that's fair game. Okay. So now looking at the next slide, this representative element, the representative rectangle, is a very important thing, because what we're doing for the remaining sections of this chapter is we're going to find an appropriate representative element, and we're going to be able to use a pre-calculus formula like area of a rectangle, something you already know, and sum up or accumulate these representative elements with a sigma, and then force the number of those rectangles, or whatever they are, representative elements is what I should have said, to be infinitely many of them, which will take you to an integration formula, which you can then integrate to find the answer. So on the next slide, the pre-calculus formula we knew was area is height times width. The representative element was the length of the rectangle f of x minus g of x times its width delta x, and that led us to the definite integral from a to b of f of x minus g of x dx for the area between the two curves. Okay, so example 6. I hope I have enough room on my slide for this. It says, just a second. All right, so I was looking, and I think I have enough room to fit this in, because I didn't want to open up a whole nother recording just to do one little example. So I'm going to try to use every little inch of space I have here. So this is example 6 below this. It says, find the area of the region bounded by the graph of y equals 4 minus x squared and the x-axis. Describe the integration as an accumulation process. So we know that if we graph this, it's going to look something like this. And that means that we're going to have to find, if we're finding between that curve and the x-axis, all of a sudden that means that the x-intercepts become important, because that's going to be where the region starts on the left and ends at the right. So that's when y equals 0. So solve that equation for x, and you'll get x is equal to plus or minus 2. So obviously this is negative 2 to 2. All right, so the area is going to be, this is a calculus 1 problem. The accumulation of the accumulation process is the thing I want to focus on, is the integral from negative 2 to 2 of our function 4 minus x squared dx. Okay. So to find this as an accumulation of area as we go, imagine that when we start out and we integrate from negative 2 to negative 2, in other words, we haven't moved from the first point. Well, obviously, not having moved at all, we've not accumulated anything, and that will be 0. And of course, this is a property that you learned in Calculus 1 for integrals. If you're integrating a function, a definite integral from a to a, the answer is always 0. So that totally makes sense to me. So we're going to start out with 0. Then we could move just a bit to the right. Let's say we move that far, and we will have accumulated area as we go by adding rectangles from 0 to 1. I'm sorry, from negative 2 to negative 1. I can talk sometimes. And if we, and I'm just going to give you the answers. I don't really need for you to calculate these. This one ends up being 5/3. Okay, and then move a bit further to the right, and we'll have what we already found, this part here, plus let's now go over to 0. We're going to accumulate more area and add this to what we already had, and so this will be starting at -2, go to 0. And that ends up being 16/3. Then we could go up to 1 this time. So we already know what the answer is through here. So now we accumulate more by going to 1 and adding this to what we already have. And that would be found by taking the integral from -2 to 1 of f of x dx. And so as we go further and further right, we're just accumulating more and more area and adding to what we already had. This ends up being 9. And then the whole thing, I'm not going to draw a picture for that because it's basically this picture, get the whole area of the whole thing, is this integral that we have up here, which has an answer of 32/3. Now again, this is a chance for you to practice Calculus 1 stuff, find the antiderivative, do the substitutions, do the subtraction, and make sure that you understand. Maybe for 1 or 2 of these, just practice doing that integration. Probably one of them is sufficient, because you are going to have to do some of these integrations yourself without technology. Now, what a boon technology is, though. We know how to find the definite integral with that FNINT, that Math9 command. And so that's a good way to check yourself if you're doing homework or something. But on a test, just be aware that you will have to do something that maybe is about as difficult as this one that we just completed, the 32/3. You need to be able to do that one completely using all of the steps. So make sure that you have that ability. Okay, so that ends section 7.1. I will see you in class.